It will begin in a moment. Yeah. Yeah. What was number 9 from our open book test? How was the question like?
So I think the surface charge density was zero, and why is the volume charge not zero in uniform polarization?
Is it that way or the other way around? Just actually, it should be the other way around. Did I have any typing mistake? I don't think so. Let me check once. Hold on.
Okay, sir.
Okay, I'll better share my screen so that you can see the question yourself. And if anyone else has any other doubt, it could be. That's why I am taking two classes today. Okay, one is for Prajjal sir's. He would be joining on Monday. He's okay now. Um, is my screen visible?
Yes, so
Yes, sir.
I mean, the Moodle screen. Can you see the
Yes,
question paper?
yes, sir. Yes,
Acha,
sir.
acha. So number 9. Yeah, no. Question is correct. It says that the volume charge density of bound charges is zero, but the surface charge density of the same means of bound charges is not zero, non-zero in case of uniform polarization. Why? Acha, anyone else has any other question from this thing? Just tell me. We can just then pick up the questions and discuss the solutions.
number 8, sir.
Number 8. Okay. Number 8, dipole moment to unit volume of polar substance is absence of polarizing field is zero.
And
Okay.
number six, sir.
Number 6 as well. Number 6
Yes, sir.
also.
Yes, sir. Like I could not like if this is the statement like the same thing as in Gosper in a free space, sir. I just wanted to know that, sir.
Acha, acha. I gave it on purpose. Actually, there is something, the Gauss law in normal electrostatics goes like this, the flux kind of thing, isn't it?
Yes, sir. I wrote something like the closed surface integral of electric
Yeah,
displacement vector. I wrote something like that, sir.
yeah, that's okay. That's correct. Is equal to, what did you write? Is equal to?
I didn't write, sir. Equal to is I wrote is proportional to the free charge enclosed by the surface in a dielectric medium, sir.
It's actually equal to, okay. Being proportion
Okay.
also means the same
Oh,
thing.
yeah. Okay, sir.
But yeah, equal to would be better. Anyways,
Okay.
okay, number 6, number 8, number 9. And girls, do you have any queries from here? Any question that you couldn't solve or you were confused? Please tell me. Arianjali and Tithi.
So for that, and sir,
Yes.
can you define that bound charges, sir? I wrote something, but like I could not define it properly, sir.
Acha. Okay.
Number three.
Number 3, define
Like
bound charges. Actually, they are the polarization charges only. They're also called bound charges.
yes, I wrote something, but like, is it correct or not? And like,
Okay.
it's a bit
Uh,
confused.
okay. Fine. So we have number 3. We are confused with the definition of bound charges, the statement of Gauss's law in dielectrics, absence of dipole moment per unit volume, and bound and volume and surface charge densities. Okay, no problem. Let me stop the presentation. Yeah. Okay, so okay, first number 9 came up. So let me do that. Number 9. So number 9 was why bound charge density is zero, or bound volume charge density is zero, but bound surface charge density is non-zero for uniform polarization. Okay, so that picture which we made, isn't it? When uh, a polar material or any non-polar material also be there, no problem. We took it with polar. So this happens when we are putting this dielectric in a electrostatic field. The plate on the left is at positive potential, the other one is at negative potential. Obviously, that is how the charges should move when they are attracted. Okay. So what is this is something, this is a case of uniform polarization, whereby you can see in the volume. Volume means what? First you have to understand what is surface. Surface or edge is something that is just at the boundary. You may think it is a wall. What is there on the wall? That is the surface charge densities. Okay, these are on the surface, and the remaining apart from that is the volume. These are the surfaces. Clear? So you can see in the volume there are equal number of positive and negative charges, so that positive negative positive negative positive negative, they overall cancel out each other. So in case of uniform polarization, what happens? The neighboring dipoles, okay, these dipoles we can call them as molecular dipoles as well. Molecular dipoles, what they do, they tend to cancel out each other, tend to cancel out each other. Okay, when dipoles are getting being cancelled out, there won't be any as such accumulation of charge in the volume. Did you understand this thing? Tell me first if this thing is okay with you or not.
Yes, sir.
Now what happens, come to the surface. So you can say that, so there is no accumulation of bound charges in the volume. The dielectric specimen. Yeah, prior to this, you may write briefly in one sentence that what is being done. We are putting a dielectric material in an electrostatic field subjected to uniform polarization. Hence, the volume bound charge density in this case is 0. Don't just copy blindly. Try to understand and then write. Done, everyone? Is it okay?
Yes, sir.
Now, what happens at the surface? However, at the surface, such cancellation is never possible. Whenever there is some cancellation, that means some n number of things are cancelled by n number of opposite things. Their effect is being cancelled. But on the surface, you can have only one layer of charges. You can't have different layers of charges so that they will cancel out each other. Okay, it's not possible. Hence, the surface bound charge density is always non-zero. Got it?
Yes, sir.
So this is how you should write the answer. So that is the answer to question number 9. So what was question number 8? It was asking that why in polar molecules the dipole moment per unit volume is 0. Because polar molecules, as the name suggests, they should have dipole moments inside them. And if you are very fast with your writing, then if this question is of 2 marks, then you can draw this picture. This diagram would make things even more clear, provided you are very fast with your writing. Okay. If it is for 3 marks, definitely you should draw this diagram. Then the teacher will understand, yeah, this student could really understand everything, and then that's why he could write. He or she didn't mug up. Okay. So what was the next question? The absence of dipole moment per unit volume. So you may write it like this. In a polar dielectric, there exists molecular dipoles within the specimen. But in absence of an external electric field, and due to thermal agitation, these dipoles are randomly oriented. within the specimen. Hence, the dipole moment that is the net dipole moment per unit volume is 0. Another way to write answers effectively, I shared a PDF, if you remember, in the last sem on Moodle, how to write answers so that you can score better than others. See, this thing, I am assuming 80% students who will attempt will write like this. Okay, but think from the examiner's point of view, he or she has to read everything line by line. And uh, after checking so many copies, that may be a boring task. What you can do? You can do this thing, you can underline the main parts. Like, what are the main things? The absence of external electric field and thermal agitation. These are the two things responsible for this happening, isn't it? So if you write it like this, then it would be easier for the examiner to check. And since you are saving the examiner's time and making things easier, you may expect better score. Is it clear?
Yes, sir.
Okay, and what was the other question? Gauss's law was one, and number 6 was what?
Number 6 was Gauss's law.
Oh, number, oh, bound charges number uh, 3. The bound charges are very simple to define. Like this, that the charges which appear in the volume no let me write with the surface at the surface and in the volume. Now within bracket you may write only for uniform polarization in a dielectric are called bound charges. Simple as that, nothing more, nothing less. So here also you can see you have specified that it's not that always in every situation it will appear in the volume. It may appear only at the surface if it is non-uniform. And what is the difference with from how is it different from free charges? Free charges can move up to uh, any distance, okay, up to macroscopic distances. But to say macroscopic distances, but bound charges cannot move over macroscopic distances. In that regard, they are bound.
Excuse me, sir. So for non-uniform,
Hmm?
bound charges appear at. So for non-uniform polarization,
Mm-hmm.
bound charges appear at both, sir.
Yeah, at the surface and in the volume as well.
So even in uniform.
No. In uniform here also, here only we saw na. In uniform, everything is getting cancelled in the volume. See, equal number of
Yes,
positive and
yes.
negative charges. But in non-uniform, there may be some asymmetry or inequality of positive and negative charges at the volume. That will render some accumulation of charges at the in the volume only for non-uniform. So that's why you have specified also. So you see if this uh, definition is worth 2 marks. 1 marks you can get 1 marks without writing this also. But if it is for 2 marks only defined, then this will give you 2 out of 2. Only if definition is being asked. So these are some tricks how to make your answers more effective.
So then it should be non-uniform. So in brackets,
No, no. These charges will appear in the volume only for uniform. For non. Oh, sorry. Right, got it. Sorry. Yeah, thank you, Adesh. Yeah, only for non-uniform, volume charges will appear. Sorry, I made you confused. Right. For only for non-uniform polarization. Yeah, now it's correct. So for non-uniform polarization, it will appear. Okay. And Shravan, the one that you wrote, that would be correct. That the closed surface integral of electric displacement vector is equal to the free charge bounded by the
Oh,
surface,
oh, okay.
enclosed by the
Okay, sir.
surface.
So for this one also, like for this bound
Hmm?
charges, I can write like the charges which appear at the surface
Hmm?
for uniform polarization and at which appear at the surface for polarization for uniform polarization and
Hmm.
at surface and volume for non-uniform polarization.
Yeah,
Also,
that also you can write, but you have to. Your sentence will be lengthier in that case.
oh, yes,
Hmm.
I got it.
Yeah, it's okay. That's so. If you can remember like that, you may write. No problem.
Okay, sir.
Okay. And so I think the doubts have been cleared.
so for number 7, like how does the tangential surface behave? No, sir. Components.
Uh, how do the tangential component electric
Tangential
hmm. You have to just write that across the interface, the tangential components of electric field vector are continuous.
continuous. Okay, sir.
Continuous. Then you may just briefly draw the picture and write the expression. Okay, that picture that we had drawn.
Okay, sir.
Okay, you may draw it like that. Yeah, with the drawing, you need not to draw that Gaussian surface thing. You can draw it simply like this. You have an interface, say S1, S2. You can define it like that. Say here medium 2, this is medium 1. And suppose this direction is normal to the surface. And these are the electric field vectors. Say E1, making an angle theta 1. Sorry, E2, making an angle theta 2. And you can write that E2 tangent is equal to tangential component is E1 tangential component. That is, you may write it like this: E2 sin theta 2 equal to E1 sin theta 1. That would be enough since 2 marks were given. Okay, like this.
Okay,
Or you
sir.
may,
So
yes,
we can write the other expression. So tan theta 1 by tan theta 2.
no. That is the cumulative effect. That
Okay,
is,
sir.
see there you are taking two things into account. You are taking the normal
Uh,
components as
yes, sir.
well as you are
And the
taking another special
tan initial.
case where sigma is 0. But this thing is true whether sigma is 0 or not at the surface. Whether charges are there on the surface or not, this thing is always true. That also you may write. If you don't want to draw the picture, you may comment it like this, that this condition holds whether surface charge density at the surface is 0 or not. Okay. Just I want to tell you that whenever 2 marks is being offered for a question, hmm, it's say it's a definition only or only a condition. If you feel that that condition is very brief, then with After finishing that condition, you may uh, write something more on that little bit so that your 2 marks is confirmed. Okay. So I
Okay,
think
so
that's all. Yeah. Anything else? Any more doubt from anyone?
So this theta one and theta two is like angle between the perpendicular component and the
Yeah. Actually, perpendicular
E
would be called the normal,
temperature.
normal to the surface.
Normal.
Okay.
Yes,
Yeah.
okay, sir.
Like n cap minus n cap.
Okay.
Okay. Always we take the normal component, normal as the reference. That is the good thing with the surface. Okay. So let us enter into the last part of this chapter, capacitance. Actually, I think they have skipped that thing called electrostatic energy. That is also necessary, but I feel that capacitance here should be studied as an application of dielectrics. However, they can function without that. Okay. So I think you all have studied capacitors in your school days, isn't it?
yes, sir.
A capacitor in the circuit looks like this, where the length of the two lines are equal. If you make one line lengthy, another line shorter, then it would be a battery. Okay, so it's a capacitance denoted by C, and we also saw that capacitors have a good number of application in electronics, especially when we were studying that 555 timer, uh, monostable and astable. So remember that thing, there was something called charging and discharging of a capacitor that was responsible for the outputs. So capacitors are very, very important. Uh, Previously, they were known as condensers. Even today, you will see in the ceiling fans, there's a big cylindrical kind of thing inside it. That is a capacitor, but those things were called condensers before. Hmm. They play a very important role in electrical and electronic devices. So what does it do? Basically, it can store electric charge, or it can store electric energy. It is like a storehouse of charge, okay, which may be discharged or which may be charged depending on the uh, end result that we want. Okay. So in the simplest form, uh, we can think capacitor as a pair of two conductors like this. We may think it like this. Maybe there are two plates, and they carry equal and opposite charges in each plate. Suppose if here I have four positive charges, I will have four negative charges on the other plate. They will have a potential difference, and this should be independent of the presence of any other conductors in its vicinity. Okay. And this relation also, you know that the charge content is definitely proportional to the potential difference, and from there we get this relation Q equal to CV. So capacitance is dimensionally charged by potential difference, and capacitance will depend on, this C will depend on the shape size, and also the separation between the conductors. I won't write plates because it's not necessary that always we will have plate capacitor. We'll see today. But the unit of capacitance, can anyone tell me what is the unit of capacitance?
Microfarad, so
Yeah, it's farad actually. Yeah, farad, written by capital F. However, farad is a very large quantity. So in reality, we use say uh, nanofarad. 1 nanofarad means 10 to the power minus 9 farad. 1 picofarad, that is 10 to the power minus 12 farad. Okay, it is picofarad. Pico. That's the prefix. Or we can have microfarad, as others said, 10 to the power minus 6 farad. Okay, in the lab we have nanofarad capacitors. Microfarad is also there. I don't remember. I have to check once when you go to the lab. Okay, so basically, what is there in our syllabus? We have the different types of capacitances. Or so not capacitances, capacitor. Capacitor is the name of the device. So we will have to study the parallel plate capacitor. Then will come the cylindrical capacitor, followed by spherical capacitor. Okay, and each uh, you can see these are based on the geometry, different geometries, isn't it? The shape, different geometries. And again, each class will have some more things to be discussed. Okay. See, I will continue the next class also. So, do you want a break now? Do you need a break?
Sure. Yes, sir.
so
Okay. So, when shall we resume? Oh, sorry, we are getting a break anyway, na? From 10:40.
yes, sir.
Yes, sir.
Oh,
Yes, yes,
acha,
sir.
acha. No, no. Then I think I can continue a little bit more. Oh, I forgot. Actually, on the offline days, we don't have a break uh, before our last class on Saturday, isn't it? But this time round, we have to keep that in mind. Anyways, so the first type that I'll be discussing would be a parallel plate capacitor. Slowly, let me give the introduction. Um, so, what is it? Very simple. Just we have two parallel metal plates like this, and they are at some separation, say small d. Parallel plates separated by a distance d. Okay, and this distance d is small as compared to the dimension of the plates. That is length, breadth, everything. Okay. So there's a reason why we do this. So before that, we have to remember that what is the condition? There would be equal and opposite charges on both the plates. Suppose this is my plate 1, this is my plate 2. Okay, if you can't understand, you can't visualize them as plates, you can, I think, if I draw like this, it would be easier for you to understand that these are actually plates. So suppose plate 1 has accumulated positive charges. So 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. So equal number of positive and negative charges. Fine. So what is the electric field? What are the field lines? Field lines should be directed here, isn't it? That is the direction of field line, positive to negative charge, isn't it?
Yes, sir.
Yes, sir.
So now you can see there is a problem at the end. These are called the end effects. At the end, what happens? The lines may get bent because the situation is not symmetric at the end. Here you may see, yeah, there are beautifully aligned charges, but there is nothing beyond this boundaries, isn't it? So the lines may get crooked or overcrowded at the ends. So in order to minimize this effect, what we do, we actually choose this separation very small. Okay, so that you can see at the ends, these curved lines are, these lines are not that much overcrowded. Okay, so that throughout the field lines are parallel. That is, the field is uniform. Fine. That is the reason behind choosing this small separation. Now both the plates are similar. So the surface area of each plate is say A. Therefore, uh, acha, do remember this thing. The field due to an infinitely plain sheet of chart sheet at any point. Remember this expression. Electric field equals to sigma by epsilon naught n cap. Remember this thing from Coulomb's
Yes,
that
sir.
first chapter, electrostatics. That is actually what we intend to apply here. And you can see the field is uniform here. So here also we have plates, isn't it? That's why we are trying to write now the surface charge densities for the first plate. It would be plus sigma. Why plus? Because positive charges are accumulated there, or you may simply write sigma. And for the second plate, accumulation of negative charges will make this thing minus sigma, minus q by a, because minus charges have accumulated. And what does it mean? Surface charge density means charge by area. If we take this separation very large or comparable to the dimensions, we can't achieve the uniform field. And if we can't achieve the uniform field, we can't apply this thing. If you want to apply this result, your field has to be uniform throughout. And also your plate should be infinite in dimension compared to the separation. Due to these two reasons, this distance is kept as small as possible. Is it okay?
Yes, sir.
Fine. So we need to find C, isn't it? C means Q by V. That is, first I need to find the potential difference. So what is the potential difference? The potential difference between the plates is say V. How to write that? This thing, potential of first minus potential of second, and it is what? It is a kind of dV thing, isn't it? And you know that this thing is equals to E dot dr. I think you're confused. Think it this way. E equals to minus grad of V. So if V has only one direction, say r cap, so it can be written as del V dV dr, that is equals to E. So dimensionally I can have what I can have? I can have V equals to E dot dr dimensionally with an integration.
Yes, sir.
Or you can do the dot product here as well. That minus dV would be equal to E dot r cap dr. So V would be minus integration E dot r cap dr means dr vector. Okay, like that. Now what is the electric field? And the electric field would be from sorry, not from, it would be like, now how to choose the end cap, isn't it? For that, in the previous diagram, we'll select, we'll call this distance as x equal to 0. This one we will take x equal to d. Okay, so that our normal is I cap. This direction is the x axis. So that our normal would be what? Our normal would be I cap. This normal. And we can integrate from 0 to t. That is the direction of the field lines, isn't it? From here to here. Direction of field line means direction of your electric field intensity. So I cap dot dr is actually everything is in terms of x. So dot uh, dx I cap. Dx is what? Dx is a change in
What?
this direction, and this direction points I cap. Yes, anyone has having any doubt? Is having any doubt? Please tell.
So what's that, sir? E by epsilon naught, sir?
This one,
Oh, that's sigma. No, sir. No, no,
sigma,
no.
sigma. That's
No,
sigma,
sir. Sigma. Okay, sir.
sigma. Yeah. So to change the limits, so it would be sigma by epsilon 0 d. Now put the values of sigma. Only magnitude you can put. So that's q by a to d by epsilon 0. That's q d by a epsilon 0. So what is the capacitance? Charged by potential difference. And what is q is q? What is v? This thing. So for a parallel plate capacitor, capacitance is this. Actually, I made some mistake. Just a moment. I think from here I should write only epsilon. Okay, not epsilon 0, because we are studying dielectrics. Okay, that is, it's not the space between the two plates is filled with a dielectric medium. Okay, not with vacuum or air. So this is the permittivity of the dielectric, that is filling the space between the plates or conductors, better to say. We may have nothing inside that is, it may be filled with air, so that we can put epsilon 0. However, that is not a wise choice practically, because if you know that what is the relation between epsilon and epsilon 0, this, isn't it? So this thing is true always. So if I put some dielectric material, I can always increase the capacitance of the capacitor.
So in this case, you have used the positive value of sigma naught, sir,
Yeah, I
like
have
for
used
plates
only
one.
the magnitude. Okay, capacitance is a positive quantity.
Okay,
Okay,
so
it can be negative, so we have put the magnitude. Okay, so I think we need to take a break, and in the next class we'll take care of rest of the things.
okay,
Yeah,
so
basically we have application of this parallel plate capacitor. Then if possible I can wrap up with the cylindrical capacitance, because it doesn't have too many not application, too many varieties. Okay, then I think let's wrap up. Let's meet in the next class. You will find the link there only. Okay, in 63. This class I would mark capacitance 1. Next class I would mark capacitance 2, or something else, other name I will give. Okay. So if you have any doubt,
okay,
you may
sir.
put forward.
Thank you, sir.
Else we may take a break now and begin from 11:10 again.
Thank
Okay,
you,
sir.
sir.
Okay, then thank you everyone.